Okay, today's lesson is going to focus in on isosceles triangles, which we have already talked about. You can see the title, Angle-Side Relationships in Triangles. So if we take a look at our targets, we're actually going to skip the proving of these theorems, which is this first part, but we are going to talk about these theorems that apply to isosceles triangles. So specifically, I can take these theorems we're going to learn and apply them in proofs and to solve problems. And then a second idea is related here. I can determine the relationships of side lengths in a triangle based on angle measures and vice versa. So this idea in an isosceles triangle, if we look at the picture here, is that we know if it's isosceles that AB would be congruent to AC. And what we can prove, and we're not going to spend time on that today, is that if these two sides are congruent, the angles at the base of those sides are also congruent. We call these two right here the base angles. All right, so that is our new theorem. If we have two sides congruent in a triangle, then the two angles are congruent. And then it is a theorem that is reversible, so we can also say if two angles are congruent in a triangle, the sides opposite them are congruent. So let's write that out. I'm going to allow you to use some abbreviations because I actually think it's easier than saying all the words. We're going to say something like this. If two sides of a triangle are congruent, then the base angles, specifically those opposite the sides, are congruent. Or we could flip it around. If the base angles of a triangle are congruent, then the sides opposite those angles are congruent. So we could draw another picture here if you wanted to. If these are the two sides that are congruent, then those are the two angles that are congruent. So basically, if sides are congruent, then the angles are congruent. If these base angles are congruent, then the sides are congruent. And please note that we are talking about the sides and the angles that are opposite each other. Notice we're not dealing with angle A. This side is opposite this angle. This side is opposite this angle. Okay, so keep in mind it is specific angles. All right, so if you flip the page, you'll remember that yesterday in the previous lesson when we talked about isosceles triangles, we had this definition. We said if two sides of a triangle are congruent, then the triangle is isosceles. So that dealt with sides. But now we have this understanding that if the sides are congruent, the angles are also congruent. So I can change this definition and I can come up with a whole nother definition that doesn't deal with sides but deals with angles. So I can add an additional definition here that says if two angles of a triangle are congruent, then the triangle is isosceles. Or I could flip that and say if the triangle is isosceles, then two angles of the triangle are congruent. Okay? So again, if we have an isosceles triangle, those two angles are congruent in an isosceles triangle. All right, so how this helps is that it just gives us a whole nother way to prove isosceles triangle. We don't have to have two sides anymore. We can simply just have two angles. All right, so let's see how we can apply these to two proof problems here. So we have angle E congruent to angle H. That's those two. And then I have segment EF congruent to segment GH. And I'm trying to prove here that DF, this segment, is congruent to DG, this segment. So I'm leaning, based on the information I have, at trying to get those two triangles congruent. And I'm off to a pretty good start, right? Because I have this angle and I have this side. All right. Well, think about what we learned, right, on the previous page. If you pull it back up, all right, let's put it here. Right, we learned that if two sides of a triangle are congruent, then the angles are congruent, or if two angles of a triangle are congruent, then the sides are congruent. So instead of focusing for a moment on these two shaded ones that we're trying to get congruent, for a moment I want you to focus just on this big triangle and think about what we just wrote on the previous page, right? we wrote that if two angles of a triangle, a single triangle, are congruent, then the sides opposite them must be congruent. If you look at this big orange triangle, right, now we're just looking at one, I see this angle, angle E in this orange triangle, and angle H in this orange triangle congruent. So if I have two angles congruent, just like I have right here, then the sides opposite them should be congruent. Again, in the orange triangle, what's opposite angle E but DH? And in the orange triangle, what's opposite angle H but DE? So in step 2, I can say DH is congruent to DE. This was given by if angles congruent, then the sides opposite them are congruent. So what you have to remember when you're using this theorem, you're only looking at one triangle. So these two angles that happen to be in these two purple triangles also lie together in this big orange triangle. So this right here is coming from the orange triangle. If that helps, I'll put it there in orange. Okay? So let's mark that on the diagram. All right. Now I think I'm in pretty good shape. I'm back to focusing on the two purple shaded triangles there. Don't I have side, side, and an included angle? Side, side, and an included angle. So now I think I can say triangle DEF is congruent to triangle DHG. That would be side, angle, side, because the angle's between the two sides. And then DF and DG, they are corresponding sides, so they're corresponding parts of those triangles. So DF congruent to DG. If triangle's congruent, then corresponding parts are congruent. And that's all there is to that first problem. Okay? All right. Let's look at example 2 here. We have angle 3 congruent to angle 4. As soon as I mark those, I notice that they don't lie in any particular triangle. So I'm wondering how I'm going to use those. I have BX congruent to AY. Let's mark those. BX and AY. Those are parts of these two triangles. I also have BW congruent to AZ. Let's mark that on the diagram as well. BW and AZ. I'm trying to get WT, which is this big segment, congruent to TZ, which is this big segment. Well, I'm not seeing that yet, right? But I am wondering what I do with 3 and 4. So I'm looking at these two little triangles, and I almost have them congruent. It seems too much of a coincidence that they gave me two parts, and this 3 and 4 are awfully close. You need to see this in the diagram. Remember, 3 and 4, there's a relationship there. 3 is supplementary to this guy right here, and 4 is supplementary to this angle right here. So I'm going to use that whole supplement process, which starts with stating a straight angle. So angle WBT is one of them. And my other one is over here, ZAT, are straight angles. That's assumed. My next step, the second step, is to say they're supplementary. So angle 3 is supplementary to this angle, which is WBX. And then angle 4 is supplementary to this one that I dotted, which is ZAY. We know that's if angles add to 180, then they are supplementary. All right, now remember I've got two of those and I've got 3 and 4 congruent. So now my theorem tells me in that third part of this process that WBX is congruent to ZAY, and that is the if angles sup to congruent angles, then they are congruent. All right, so now I have these angles congruent. Let's mark them. Well, now I think I have enough to get these two triangles congruent, and maybe you don't realize how that's going to help you yet, but let's write that down. So triangle WBX is now congruent to triangle ZAY. And I believe that side, angle, side, right? I have two sides and the included angle. So now the question is, how does having these two triangles congruent help me to get WT and TZ? Well, they're not corresponding parts. I think a first instinct might be to look at BW and AZ, but I already have those congruent. I don't have midpoints or anything, so I can't multiply to double. That would be appealing too, but I would need to know B and A are midpoints, and I don't have that information. So the question is, what corresponding part of these triangles is going to help me get this? Well, once again, think about what we're working on in this section, right? We know if sides are congruent, then the angles are congruent, and if angles are congruent, then the sides are congruent. So let's look at what we need here. We need WT and TZ. We need these. All right? We want to get the sides. That would be like saying here, I want to have these two sides congruent. If I want to get those two orange sides congruent, I'd have to have these two angles congruent. I believe in my diagram that's W and Z. But don't I know angles W and Z are congruent because they are corresponding parts of my triangles? So that's the trick. From these two shaded triangles, I'm going to say angle W, and I can do that because there's only one angle here, congruent to angle Z, and again there's only one angle here, by if triangles congruent, then corresponding parts are congruent. So now if I have this over here congruent to Z, now I have the scenario. I have these two base angles congruent in this big, let's close it off here, triangle, right? In this big triangle, I have these two angles congruent. That's the scenario. So if those angles are congruent, now those those opposite sides are congruent, these two orange pieces. So WT is congruent to TZ because if those base angles are congruent, W and Z, then the sides opposite them in this big triangle are congruent. And I can simply use those symbols when I write my theorem. Okay? All right. Let's flip the page. We're going to come back to the other two examples in another video. So we're going to jump right ahead to this one right here. It says, in the triangle below, estimate the measures of the angles and label them A, B, and C, where A is the largest and C is the smallest. So I think we can do that to start. That definitely looks like the biggest angle. I'm going to guess, I don't know, it's somewhere between 90 and 180, so I'm going to guess like 150. All right, and you might guess something similar. This looks like the next biggest angle. To me, that looks like maybe half of a right angle or maybe a little more, so I'm going to say that that is, oh, I'm sure this isn't 150. Let's make this 110 actually. I made that way too big. Let's call this 110. Right, somewhere between 90 and 180. And then I'm going to call this one 50. And I know the angles in a triangle have to add up to 180, so this is 160, so that would leave about 20 for that one. I hope that makes about sense. Now it also says to estimate the sides, so I have a ruler here. So if I approximate this segment over here, this is about 11 centimeters. This one down here is roughly 13 centimeters. And this segment AB on the side, that's about 4.5 centimeters. And again, we're just approximating so that we can notice some relationships. It says, what do you notice about the relationship between the largest angle, now remember the largest angle was A, and the largest side, that was 13. So when you look at the largest angle and the largest side, you should notice that they're opposite each other. If I'm at angle A and I go straight across, I hit the longest side, right? Similarly, the smallest angle and the smallest side. So here's the smallest angle. If I go directly across, I hit the smallest side. And here's the one in the middle, right? The medium angle goes straight across to the medium side. This will always be true. So we're going to make this a theorem that you're going to see on the next page. So if you flip here on the screen here, we're going to say if two sides of a triangle are not congruent, then the angles opposite them are not congruent. All right, so it's unlike the isosceles version. If isosceles, if they are the same, then the angles are the same, the sides are the same. Here we're saying if the sides are not congruent, then the angles opposite them are not congruent. But let's put the most important piece here, and the larger angle will be opposite the larger side. All right? We can do that the other way too. We can say if two angles of a triangle are not congruent, then the sides opposite them are not congruent, and the larger side will be opposite the larger angle. So what you really need to remember is if I have a triangle like this and I call this A, B, and C, and let's say I tell you this angle is 70 degrees and this angle is 10 degrees, right? They're not congruent. 70 and 10 are not congruent. Now we know the larger angle will be opposite the larger side, and the larger side opposite the larger angle. So 70 is larger, so that means AC, right, should be larger than what's opposite the 10 degrees, which is AB. That's what the theorem is telling you. Okay. In triangle MAT, let's look at example 5 here. TA is the longest side. MT is the middle side, so I'm just going to put here long, and then MT I'm going to put here medium, and AM, and this is the smallest side. It wants me to list the angles in order from smallest to largest. So I want the smallest angle, and then I want the medium angle, and then I want the biggest angle. All right, well, the smallest angle should be opposite the smallest side. So if this is the smallest side, I go across, the smallest angle is angle T. The medium side was the MT, right? So the medium angle should be across from it. That would be angle A. And then the biggest angle will be opposite the biggest side. This was the longest side. Across from it is angle M. So that would be the order in which I would list them, from smallest to biggest. All right. Another way we can apply that last example here is given that AC is greater than AB. So AC, right here, this guy, is the biggest, is bigger, I'm going to say, than AB. Well, according to my theorem, the bigger side should be across from the bigger angle. So that means if AC is greater than AB, the side opposite, angle B, should be bigger than this angle that's opposite AB, which is angle C. Well, I have expressions for those, so angle B is 6x minus 45 should be bigger than 15 plus x. If I subtract x, I get 5x. If I add 45 over to that side, I get 60. Dividing by 5, I have x greater than 12. Okay. We can come up with one other inequality that we often forget about. We know the angles in a triangle, right? I'm going to put this down here. Angles in a triangle add up to 180. Well, I don't know this angle right here, so I can't add all three of them up to 180. But if they all have to make 180, together these two have to be less than 180, because this plus this would equal 180. So these two must be smaller than that. So that's my other equation that I'm going to write. 6x minus 45 plus 15 plus x together must be less than 180. So that is 6x plus x is 7x. Negative 45 plus 15 would be negative 30. If I add, I get 7x is less than 210 and x is less than 30. So now if I want to write this, right, x has to be less than 30, but x also has to be greater than 12. Right, those are the restrictions that they're asking for on x. So this came from the new theorem that we had above. And this idea is that since all three equal 180, together these two must be less than 180. And that's it for right now.